So this is problem 79, chapter 6 of Giancoli 6th edition. So we have an elevator. The elevator cable breaks when this elevator of a certain mass, and this is a big mass. When this elevator of this certain mass is at a certain height, I'll call this initial position y1. And they also give us the spring constant. This elevator is above a huge spring, and they give us this spring constant. Okay. Okay. So the idea is the following: we have this elevator initially at this high position y1. The cable breaks, and so this elevator will fall and will hit this big spring. And the first question of this problem is calculate the work done by gravity on the elevator just before it hits the spring. So we have to take into account this displacement from that y1 to this y2. Okay, so this is the first question, the work done by the gravitational force. Um, we know that the work done by the gravitational force is minus the change in potential energy, meaning minus the final potential energy, the gravitational potential energy minus the initial. And this gives us then the potential energy at the final minus the potential energy at the final position plus the initial. So plus P1 minus P2. Okay, so all that we care about is the height, is the difference between y1 and y2. So this is going to be mg y1 minus y2. Okay, so this height is given to us, this difference is given to us, so we can compute this work. Okay, now part B. Part B asks the speed of the elevator just before striking the spring. So we want to know what is this V2 here. Okay, so I'm going to use conservation of mechanical energy to solve this problem. So the K1 plus P1 equals to K2 plus P2. And let me now define the frame that we are using. Okay, so I'm going to use as frame this position here, this y2 will be 0. Okay, all right, so the initial kinetic energy is 0. The elevator was initially not moving, but it had a lot of gravitational potential energy, so plus mg y1, and this y1 is given to us. Right before hitting the spring, it has now a lot of kinetic energy. That potential energy was transformed into kinetic energy. So 1/2 of mv2 squared, and v2 is our unknown. And since I chose that position y2 as being 0, then I'll say that my potential energy is 0. From here, we'll get the speed of the elevator just before striking the spring. And then finally comes the last question of this problem, which is calculate the amount the spring compresses. Okay, so after this elevator hits the spring, what will happen is the spring will compress by this amount here, which I'm going to call big Y. And the question of the problem now is by how much this spring gets compressed. Okay, again, what we're going to do, conservation of mechanical energy. The initial is equal to the final. What I'm going to consider as initial is up to us. Either I can pick this position 1 or the scenario 1 or the scenario 2 when we are right before hitting the spring. Okay, they are equal, the two. We have conservation of mechanical energy, so either 1 or 2 is the same. So either I select as my initial mechanical energy the sum of K1 plus P1, or I select K2 plus P2. It's up to us. We know that they are equal anyway. And this will be equal to the final scenario, which I'm going to call 3, after the spring gets compressed. And here I have K3 plus P3. Okay, So if let me start, let me pick as my case 1. Okay, so I'm going to start with case the scenario 1. Okay, so then what I would write is initially I just have mgy1 because my initial kinetic energy is 0 at position 1, and this will be equal to K3 plus P3. What do I have? K3 is the potential energy, and P3 may be gravitational and may also be elastic. So let's see what we are going to consider. So on the right side, I have mgy. On the right side, well, this spring will be getting more and more deformed until it stops. So the final scenario 3 means no kinetic energy, so 0 for kinetic energy. And how about gravitational potential energy? So this is one part of the energy that the students sometimes forget. But since I chose this point as being 0 and I'm now below, I need to take into account negative mgy, and y here is our unknown. Okay, so we do have to take into account gravitational potential energy. It's not just 0, I'm below point 0. And how about elastic potential energy? So we have it, we deform that spring, we compress that spring, so we have it, and this is 1/2 k is given to us, and y squared, and where y is our unknown. So to solve, we have to solve now a quadratic equation. So here on the left, we have just a number, and on the right, we find our unknown, the big Y. We have to solve this quadratic equation, and when we do that, we will find two solutions, a positive one and a negative one. Since I already took into account the signs when I wrote the equation, the solution of the problem that I'm interested in is this positive one. This is the one that we are going to select. The negative one makes no sense in this problem, so I'll discard it. So remember to take into account that there is gravitational potential energy, negative value, and remember that we will have to select the positive solution.